Hello everyone. In this lecture I shall discuss the Taylor series and Maclaurin series. Also I will discuss the radius of convergence in some standard series. Now if you recall the power series with center at Z0, right? This is converges everywhere within the circle of convergence. Z minus A mod less than R. Within this circle it will converge everywhere. Right, now if I put this is equal to my u, if I put this is equal to my u, then this power series can be viewed as an u to the power n, or simply this series can be viewed as an z to the power n. Right, here 0 is the center, right? So this 0 here is the center. Clear? Now this, if your r is equal to 0, then what will happen? The power series converges only at the center, right? It is called the point convergence, or we can say nowhere converges except at 0. Now for example, if you have n factorial by z to the power n, then if you want to find the radius of convergence, what is the formula to find the radius of convergence? R is equal to limit n tends to infinity, here an by an plus 1 magnitude. This is the way to find the radius of convergence. So now what will be a radius of convergence here? You see, so in this case here r is equal to limit n tends to infinity, here an is n factorial by, means here n factorial by n plus 1 into n factorial. It is because factorial of n plus 1 mode, right? So this is 1 by infinity is here 0 here. So means it converges only at the origin. It is called a point convergence, right? Or in general we can say nowhere convergence, right? Convergence only at a particular point doesn't make any sense for further analysis, right? Now if here r is equal to infinity, right? If r is equal to infinity, then the power series converges everywhere, or we can say converges for all z in C. If we find here similarly here r is equal to infinity here, right? So it converges everywhere. So now if z minus z mod is equal to r, or with center at 0 we call z mod equal to r. So the analysis for z mod we will also extend it to any center, right? As I have told here, putting here z minus z0 is equal to u. So if you analyze the series for this, then it can be extended to this. So now it is called the circle of convergence, where no conclusion can be done. Now we consider 3 power series. In each cases the radius of convergence 1 here. In all these cases the radius of convergence is 1 here. Now this first case, it converges everywhere, right? It converges everywhere. Everywhere here means for z mod converges everywhere within, I can say, right? Convergence everywhere within and on z mod equal to 1. So here on this boundary also, means on this it converges within the circle, within and on the circle. So here it converges here also, as well as it also converges on the boundary, right? Means here converges for z mod less than 1, also for z mod equal to 1. So on the boundary it converges here, right? As I told, no conclusion. So on the boundary it converges. In somewhere it may also diverge. Now this is this converges for, it converges, we can say at z is equal to minus 1, but diverges at z is equal to plus 1. So here if you consider this circle of convergence, here r is equal to 1. So here it will converge only, here it will converge. It converge for z mod less than 1, right? diverges for z mod equal to 1. So you see on this boundary here. So on this boundary here, not converges on the boundary. Not converges on the boundary. On the boundary. Right. Now what will happen to z mod z to the power n? So here in z to the power n, here an is 1 here. Right. So radius of convergence, limit n tends to infinity, an by n plus 1 mod is 1 here. But it converges everywhere, right? It converges for z mod is less than here 1, but diverges for z mod equal to 1. Means on this boundary here, in this boundary, it converges throughout here. Here it is converges. Everywhere it converges, but on the boundary it diverges. So that's why no conclusion can be drawn, right? On the boundary, what we see on the boundary here, it converges. Here converge on the boundary, converge on the boundary. But here it is diverge on the boundary, not converge on the boundary. And here it is not converge on the boundary, not converge on the boundary, right? That's why no conclusion can be done. So now to be specific, we will discuss the Taylor series. And before the details of my discussion, let me to introduce myself. Myself Professor S.K. Paikray, Susanta Kumar Paikray, currently working as a Professor of Mathematics at B.Sc Veer, Surendra University of Technology, Burla, Sambalpur, Odisha, India. So without much delay, let me to discuss the most awaiting Taylor series. Coming to the Taylor series expansion of a function, in view of your Taylor's theorem, we can say let fz be analytic everywhere in a domain D, and z0 be any point, right, in D, in D, z0 be any point in D. Then there exists precisely one, right? Precisely one, I can say precisely one means unique, only one, unique Taylor series, right? Taylor series with center at z0, with center at z0, that represent fz for all z in D, right, of the following form. The form is f of z for any z. You see, suppose this is your circle of convergence. Now suppose the domain D, okay, suppose the domain D, and it is converges everywhere at each and every point. It converges everywhere at each and every point, right? Let z0 be a point here, treated as a center. Now we can able to find the power series here with center at z0, right? And here radius r here, radius of convergence r here. Now for all z here, for all z, whatever z you take, for all z, right, we can find the Taylor series expansion, the series expansion of the following form: fz is equal to f of z0 plus z minus z0 f dash z0 plus z minus z0 square f double dash z0 by factorial 2 plus so on. If you continue, it will be z minus z0 to the power n f nth derivative at z0 divided by factorial n, right, and so on. It will continue, and the series will valid within this region of convergence z minus z0 mod is less than r. Here R is the radius of convergence. So that means I can say, in view of this, I can write, that means I write in the language as follows, and this expression is valid. This expression is valid in the largest open disk. In the largest open disk, Z minus Z0 mode less than R. Right, this is the disk with center at Z0, with the center at Z0 and radius of convergence R. Okay. Now to make this series simple, if I put Z minus Z0 is equal to U, right, then in view of that, what will be my power series? So Z is equal to, here Z is equal to U plus Z0, so this will be my f of U plus Z0, right, will be f of U plus U, f dash U. Now before this way of representation, I write it in proper shape. Let this coefficient be my A0, and this is my A1. In general, this is my A2. In general, this is my AN. Then what is my FZ? So FZ will be of this form. Here summation of AN is equal to 0 to infinity. Here AN Z minus Z0 to the power N. Right. With what is your AN? Where here AN is equal to this. In general, AN is f nth derivative at Z0 divided by factorial n. This is your AN. Where AN is here this. Right. But this AN has a different form, AN is equal to 1 by 2 pi I. This is your, suppose this domain is created by the circle of convergence C, right, the path C. Then it is my integral C. Here fw by w minus z0 to the power n plus 1 dz. Okay. Actually these two, right, these two can make equivalent in view of the Cauchy integral formula. But this version of this approach will be complicated here. It is complicated. Now this version is easy. This is easy version. Okay. And we successfully use some standard series to make it further easy. So now to make it easiest, we recall some standard series expansion. Right. So now here this series is valid in this domain. Z minus Z0 mode is less than R. Right. Now in view of this, if I put here Z minus Z0 is equal to U, then what is your Z? So this implies your Z is equal to U plus Z0. So what happens to this series? The series becomes Fn is my summation. Here Fz becomes my f of U plus Z0. Right. So this will be my AN U to the power N with U mod less than R. Now again if I substitute here U, then I will get U is my Z minus Z0 mod less than R. So we can come back to this original series. Right. So this approach is a better approach. Right, where U is my this. Clear? So in this approach, this standard series expansion can be used. If I bring back the center to origin with the variable u. Okay. Now I can rewrite this statement in a simple way. Suppose fz is analytic at all points on and within, because it is a closed path within the circle. C z minus z0 mod is equal to r, right? Then, or I can write less than is equal to r. So since I have taken this within, right, within the circle, within z minus z mod is equal to r, means inside and on, right? Then at each point z inside C, then at each point z inside C, we have fz is equal to f of z0 plus z minus z0 f dash z0 plus so on z minus z0 f nth derivative at z0 by factorial n plus so on, or that is equal to, I can write it summation of an z minus z0 to the power n with z0 belongs to C, right? Z0 in C, Z0 is the center, with Z0 is the center, right? Is the center, means we have, this is the circle of convergence here, this is C and this is my Z0. It is analytic everywhere, right? It is analytic everywhere with Z0 is at the center. So at Z0 is a point of analytic. So with Z0 is the center. Now if this Z0 is a point of analytic, it is also an analytic point. Fz is analytic at Z0, right? Now if it is not analytic at Z0, not analytic will lead you towards the Lorentz series. If it is not analytic at Z0, then Lorentz series expansion required. Lorentz series expansion needed. We will discuss in the next lecture, okay? So we will discuss in the next lecture, but here it is analytic, otherwise we cannot move, right? Here an is equal to f nth derivative at z0 by factorial n, okay? So this is what my simplest way to write the, and this Taylor series is unique. Now coming to the remark, I can say Taylor series is unique by any means. You find by direct remembering the standard series, or you apply this, whatever method you apply, the Taylor series is always unique. But the Lorentz series is mad unique. I will discuss in the next lecture. If Z0 is an isolated singular point, right? Now how to find the radius of convergence? The radius of convergence R is the shortest distance of Z0 to the nearest singular point of fz. Okay, so this is most important, shortest distance. If I ask you what is the radius of convergence of, suppose tan z is a series, for example, suppose my fz is equal to tan z. If you recall the expansion, it is z minus zq by factorial 3 no, factorial is not there. Z cube by 3 plus 2 Z5 by 15 in that way. Okay, you apply minus. So if you apply this series expansion, you will get it. Now what is the radius of convergence here? Since I am not getting a pattern of an, what is the radius of convergence? You see, tan z is here sin z by cos z. So cos z is equal to 0. It is not analytic when denominator 0. Cos z is equal to 0. So this implies z is equal to here plus minus pi by 2 plus minus 3 pi by 2. So this is the shortest distance here. So what is your r here? R is pi by 2 because you are taking the absolute value, right? So r is pi by 2, the radius of convergence. So I can write here z mod is less than pi by 2, right? I can write here z mod is less than pi by 2. Similarly, if I ask, suppose fz is equal to here 1 by 1 minus z. So within no time I can say it is not convergent at 1, right? It is not analytic, not defined at 1. So here z mod is less than 1. The radius of convergence is 1 here. It is no, you know this binomial expansion 1 plus z square, but here we are getting a pattern summation of z to the power n, right? So here we are getting a pattern. So this analytic point, right, the failure of analyticity, the singular point, and the smallest point will give you from this center will give you the radius of convergence. Okay, so coming to an example, find the Taylor series expansion of sin z about z is equal to pi by 4. Okay, your sin z is analytic everywhere, right? It is an entire function. So here we need the center z minus pi by 4 mode. Okay, we want to find it, and by inspection I can say it here. By inspection I can say it here infinity. The radius of convergence is infinity here because sin z is analytic everywhere, right? So how to find it? So now if I apply the formula, what is my fz? It is my f of z0 plus z minus z0 f dash z0 plus z minus z0 square f double dash z0 by factorial 2 plus z minus z0 cube f triple dash 0 z0 by factorial 3 and so on. It will continue in that way, right? What is my z0? So here my z0 is pi by 4. So I need to find the compute all these things. So fz is equal to sin z. So that means my f of pi by 4 is my sin pi by 4 is 1 by root 2, and my f dash z is derivative of sin z is cos z. So my f dash pi by 4, it will be my cos pi by 4 is also 1 by root 2. So what is your f double dash z? F double dash z is derivative of cos z is minus sin z. Okay, so your f double dash pi by 4 is minus 1 by root 2. Okay, similarly here f triple dash z is here minus cos z, implies f triple dash pi by 4 is here minus 1 by root 2. So in general, if I continue it here, what is your fnz? Here fn nth derivative of z is sin z plus n pi by 2. Okay, sin z plus n pi by 2. And so what is your f nth derivative at pi by 4? It is your sin pi by 4 plus n pi by 2, right? So that is equal to, I can write sin 2n plus 1 pi by 4. In that way I will write the general term. Okay, now you see this is a difficult task to find this function is simple, right? Complicated due to difficult or lengthy to compute derivatives f dash, f double dash, so on fn, right? So we prefer direct method. We prefer direct series, right? We prefer direct series. Later on I will discuss in another example. Thus the Taylor series expansion is given by, thus the Taylor series expansion is given by here fz is equal to f of 0 is here 1 by root 2 plus z minus pi by 4 1 by root 2 plus it is minus z minus pi by 4 whole square by factorial 2, because it is minus 1 by root 2. In that way it will continue. So this is equal to here 1 by root 2, it is 1 plus z minus pi by 4 minus z minus pi by 4 whole square by factorial 2. Next is also minus z minus pi by 4 whole cube by factorial 3. So on it will continue. Okay. So now in general I can write it. So in general we should write it an z to the power n in general, or we have summation of n is equal to 0 to infinity here z minus pi by 4 to the power n years by factorial n sine 2n plus 1 pi by 4. Okay. So here we get it sine 2n plus 1 pi by 4 is here fn. So fn z by factorial n, it is of the form an z to the power n. An is what? An is here fn z0 by factorial n. So this is my an here. So this is my an here. Right. So what is my an? My an is sine 2n plus 1 pi by 4 by factorial n. Then what is my an plus 1? An plus 1 find, and I find what is my radius of convergence? It is limit n tends to infinity an by an plus 1 magnitude. If I simplify it, I will get it infinity. Okay. Because and by inspection also I can say, right, by inspection I can say that sin z is analytic everywhere, right. So the radius of convergence is infinite, right. So you see here, even if it is simple to find the derivative, but it is complicated. Now alternatively, if I apply the series technique directly, right, means you put your center is pi by 4, z minus pi by 4 is equal to u. So that means here fz is equal to here u plus pi by 4, u plus pi by 4. So what is your fz? Fz is equal to sine z is here sine u plus pi by 4 z. So what is your z? Z is equal to, sorry, so what is your z? Z is u plus pi by 4, it is u plus pi by 4. So now it is sine a plus b, sine a cos b, sine u cos pi by 4 plus cos u sine pi by 4. Okay. So sine pi by 4 and cos pi by 4, these are root 2. So 1 by root 2 here sine u plus cos u. Right. You might have remembered the formula here. The expansion of what is sine z, you know it is summation of minus 1 to the power n z to the power 2n plus 1 by factorial 2n plus 1. You should remember it. And here cos z is summation of minus 1 to the power n z to the power 2n by factorial 2n. Okay. And here in each cases, here z mod is less than r. Radius of convergence is r. Right. This radius of convergence is r here. So what we are getting? So we can apply the formula for sin u and cos u. So this will be here 1 by root 2 sin u is minus 1 to the power n u to the power 2n plus 1 by factorial 2n plus 1, right. And here accordingly here summation of minus 1 to the power n u to the power 2n by factorial 2n plus 1. This is your factorial 2n, or if we can combine them also. So this is 1 by root 2, right, summation of minus 1 to the power n, it is u to the power 2n plus 1 by 2n plus 1 factorial plus it is u to the power 2n by factorial 2n. Okay, with here u mod less than infinity. So now we just substitute where my u is equal to z minus pi by 4. Just I substitute it. So this is my answer, right. So if I remember some standards power series expansion here, Taylor series expansion here, then it is quite easy. We can avoid the derivative. Okay. So now this Taylor series about origin, if center is origin, then it is called a Maclaurin series. So let me write the Maclaurin series. Now Taylor series about origin, right, that means at center z is equal to 0 is known as the Maclaurin series. Here center is 0 here, right? Then it is convergent, analytic everywhere, right? So it takes the form here fz is equal to f of 0 plus z f dash 0 plus z square by factorial 2 f double dash 0 plus dot 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 z to the power n by factorial n f nth derivative at 0 plus so on, with here z mod is less than r, or we can write it summation of n is equal to 0 to infinity f nth derivative at 0 by factorial n z to the power n, and this is my an now. So this is my summation of an z to the power n is equal to 0 to infinity. Okay, now we will write some standard Maclaurin series. Now coming to some standard series, here e to the power z is 1 plus z square by factorial 2 plus z cube by factorial 3 plus so on, and we can write it summation of z to the power n by factorial n, right? If we find the radius of convergence, you see e to the power z is analytic everywhere, right? So the radius of convergence should be infinite, right? The radius of convergence here I can write it z mod is less than infinity. So if I want to prove it, what is your an? What is your an? An is 1 by factorial n, is not it? An is my 1 by factorial n. 1 by factorial n. An plus 1 is 1 by n plus 1 factorial. Okay. So 1 by r is equal to limit n tends to infinity. I am writing 1 by r. So it is an plus 1 by an magnitude. Okay. So this is equal to an plus 1 by an. N factorial by n plus 1 factorial. Okay. So limit n tends to infinity. So what I am getting? I am getting it is limit n tends to infinity 1 by n plus 1. So this is equal to my 0 here. So 1 by r equal to 0 implies what is your r? Implies your r is equal to infinity. Okay. So as I have told, the radius of convergence is the distance. So from 0 to here the nearest singular point is no singular point, so it is infinite radius, right? So now if you are e to the power minus z, it is just plus minus 1 minus z plus z square by factorial 2, and it will be minus 1 to the power n z to the power n by factorial n with z mod less than infinity. So now coming to your logarithmic series, it will be here 1 minus it is your z. If you expand it, it is your fz, right? If here it is your fz, so you find f of 0 plus z f dash 0 plus z square by factorial 2f double dash 0. In that way, if you go on continue, you see this is not analytic when this is 0, log 0 is not defined. So here, right, at z is equal to minus 1, it is not analytic, right? So the nearest singular point is minus 1. So what is the distance? The distance is here 1 here, right? The radius of convergence is 1 here. So now if we expand it, what will be my series? It will z minus z square by 2 plus z cube by 3 minus z 4 by 4, right? So on alternatively. If I find now what is your log 1 minus z, log 1 minus z will be, all the sign will be minus here, z is replaced by minus z, right? Here z is just you replace z by minus z, so then all are minus of z square by 2, because minus of z whole square, minus of z cube by 3, minus of z 4 by 4, right? So all are minus, and I can write it here, summation of minus 1 to the power n minus 1 z to the power n by n. Okay, z to the power n by n. This is here z to the power n by n. N is equal to here n is equal to 1 to infinity. N is equal to 1 to infinity with z mod less than 1. Similarly, I can write it here. So now here also z mod less than 1. Now if I add these two, then if I subtract these two, then I can generate. So coming to your sin z, it is most familiar. You know it is z minus z cube by factorial 3 plus z 5 by factorial 5 minus z7 by factorial 7, so on alternatively. So it is minus 1 to the power n z to the power 2n plus 1 by factorial 2n plus 1. Okay, summation n is equal to 0 to infinity. And here the radius of convergence is infinite, right? Because sin z is analytic everywhere. Or if you find by taking this coefficient, you take this coefficient here and you since this power is 2n plus 1, you can find your r square is equal to limit n tends to infinity an plus 1 by an mod, and you get it here infinity. So here r is equal to infinity. Okay. Similarly, what happens to your cos z? Your cos z will be z square minus, it is actually here 1 minus z square by factorial 2 plus z fourth by factorial 4 minus z 6 by factorial 6, so on. So you can write it summation of minus 1 to the power n, right, minus 1 to the power n z to the power 2n by factorial 2n with z mod less than infinity, n is equal to 0 to infinity. Now if you find your sine hyperbolic z, now coming to your sine hyperbolic z, okay, so all will be positive, no negative sign. So this, and here the radius of convergence is same, infinity, right, and cos hyper, because you know sine hyperbolic z is minus I sine iz, similarly cos hyperbolic z is cos iz, so here also the radius of convergence is infinity. And tan z, okay, this is your pi by 2, because as I have told you here, tan z is your sine z by cos z. Cos z is 0, z is pi by 2. Similarly, tan hyperbolic z is sine hyperbolic z by cos hyperbolic z. Okay, cos hyperbolic z is 0, means cos iz is 0. So z is here pi I by 2. But the magnitude we are taking, we are getting pi by 2. So it is here also pi by 2. Now we'll see the binomial series. Now coming to the binomial series, actually these are most important. These are very important for series expansion. Okay, we'll use this in both Taylor series and Lorentz series, 1 by 1 minus z, right. This is here 1 plus z square plus zq, so on. So this is summation of z to the power n, and you see it is not analytic at z is equal to 1, so z mod is less than 1, right. So here 1 by 1 plus z, so z is replaced by minus z, it is alternatively plus and minus, right. So it is here minus 1 to the power n z to the power n, it is also z mod less than 1, right. Now in view of this, suppose I take 1 by 1 minus z to the power k, then what will happen here? It is summation of z to the power k whole to the power n, and in view of this you write z to the power k mod less than 1. So this is same thing as z mod less than 1. Okay, and in view of this you can write 1 by 1 plus z to the power k, it is summation of minus 1 to the power n z to the power k whole to the power n with z to the power k mod less than 1 is same thing as z mod less than 1. Similarly here 1 by 1 minus z square, it is 1 plus 2z plus 3z square plus 4z cube, so on with z mod less than 1, Now coming to another important series, 1 by 1 plus z whole to the power k. Okay, this is actually 1 minus z whole square, this is 1 plus z whole square. So this will be here summation of this power, I am taking k here, combination of n plus k minus 1 k, and it is because of it is plus, it is minus 1 to the power n, okay, z to the power n, z mod less than 1. Here n is equal to 0 to infinity. In binomial series you find the radius of convergence in 1 here. Now similarly, if I have suppose my 1 minus z to the power p whole to the power k, then thus just here, because it is minus, there is no minus 1 to the power, it is combination of n plus k minus 1 k, z is replaced by simply z to the power p whole to the power here n, okay, z mod less than 1. So suppose coming to a simple example, you are asked to find the Taylor series expansion about origin and about z is equal to 1 for this function this, and find the radius of convergence. If you come to solution of 1, what is your fz? It is your f of 0 plus z f dash 0 plus z square by factorial 2 f double dash 0, and so on. If you find it, you will get it summation of z to the power n by factorial n, right. And define the radius of convergence here. Here an is here 1 by factorial n, so here 1 by r is limit n tends to infinity an plus 1 by an magnitude. If you simplify it, you will get it infinity. Okay, now coming to your solution 2. In solution 2 you have you are given that center is at 1. Okay, so what is the Taylor series here? Here fz is equal to f of 1 plus z minus 1 f dash 1 plus z minus 1 square by factorial 2 f double dash 1 plus on. And if you find what fz is e to the power z, so this implies here f of 1 is e, f dash z is also e to the power z. You find f dash 1 is 1, e, all are e. Okay, so what is here fz? So here e to the power z here is here e into 1 plus z minus 1 plus z minus 1 square by factorial 2 plus z minus 1 cube by factorial 3, so on. And accordingly you write e summation of n is equal to 0 to infinity, it is z minus 1 to the power n by factorial n. Now we find the radius of convergence here. So here an is here e by factorial n, accordingly you find an plus 1, it is e by n plus 1 factorial, and you find your r is here infinity here. But I want to say here, you should use the standard series. Since the derivative is easy, it's okay. Now we use the standard series expansion. Alternatively I can use here, right? So here in the power of z minus 1, so z minus 1 mod we need, this means z minus 1 mod less than infinity we are getting. So here what we are doing, we we reshift the center, right? We reshift the center. You put z minus 1 is equal to your u here. So z is equal to u plus 1. So now what is your fz? Fz is e to the power z. So here e to the power z is e to the power u plus 1. So this is equal to e into e to the power u. Now you apply the expansion here. So this is equal to e summation of u to the power n by factorial n with, you know, u mod is less than infinity because expansion of e to the power u. So you just write e summation u is z minus 1 to the power n by factorial n with z minus 1 mod less than infinity. You see, now it is quite easy now. If you remember this standard series, then it is quite easy now. Okay, now let me to solve one more example. Now coming to one important question. Here fz is equal to this. So solution, here fz is equal to z minus 1 by z plus 1. So you can write it 1 minus 2 by, so since the denominator is z plus 1, in the numerator you write z plus 1 minus 2 by z plus 1. Okay, so this is 1 by z plus 1 minus 2. So sorry, so you will able to write it. You see, you will able to write it here. This by this is 1, so this is equal to 1 minus this by this is 2 by 1 plus z. Okay, so now this is fz. Now we apply the binomial expansion here for your solution 1 about center 0. So we just write it. So this is my 1 minus twice 1 by 1 minus z summation of z to the power n simply with z mod less than 1. So this is equal to 1 minus summation of 2 n is equal to 0 to infinity z to the power n with z mod less than 1 is your answer. Now if you find derivative, then it is quite lengthy, f dash f double dash. Okay, so this is the answer. Now coming to the solution of 2i about z is equal to 1. So you put, we need z minus 1 mod less than r we need. So you put here z minus 1 is equal to u, implies z is equal to your 1 plus u. So what is your fz? So fz is equal to your 1 minus 2 by 1 plus z. So it is equal to your 1 minus 2 by, right, 1 plus 1 plus u. So this is equal to 1 minus 2 by 2 plus u, right? So we will write it, this is 1 minus, it is 1 minus 2 by, okay, taking 2 common here, it becomes here 1 plus u by 2, 1 plus u by 2, right? So this 2 and 2 cancelled here. So this is equal to simply 1 minus 1 by 1 plus u by 2. If you think u by 2 as your x, it is 1 by 1 plus x. So this is 1 minus summation of minus 1 to the power n u by 2 to the power n with u by 2 mod less than 1, right? So that is equal to, you can write it summation of minus 1 to the power n is equal to 0 to infinity. It is u. What is your u? U means here z minus 1 to the power n by 2 to the power n with z minus 1 mode is less than 2. So the radius of convergence is 2 here, right? Is that not easy, right? But if you find the derivative, f dash, f double dash, f triple dash, so on, it is quite lengthy and difficult, right? Lengthy and difficult. So by remembering certain binomial expansion formula, it is quite easy. Let me to solve one more example. So now we are asked to find the Taylor series of this. Now if you want to find the Taylor series, it is f of I plus z minus I f dash I plus z minus I whole square by factorial 2 f double dash I. Okay, you see, it is quite a lengthy and difficult approach, right? But if you remember this series, what we do? We just put. We need the center at minus I. So z minus of minus I, z plus I is equal to u, just we put. So what we are getting? So here z is equal to u minus I. So what is your fz? Fz is equal to here 1 by z plus 1 whole square becomes here 1 by z is u minus I. So u minus I plus 1 whole square. So this is equal to 1 by, it is 1 minus I plus u whole square, right? We want to make it 1. We want to make it 1. So we take common 1 by 1 minus I. 1 minus I taken common here, right? 1 minus I taken common. Since whole square is there, it is whole square will come out. So this becomes here 1 and this becomes here u by 1 plus I, right? So this is to the power minus 1. Now this becomes here constant. So it is in the denominator. So it is in the denominator. So this is equal to 1 by 1 plus I whole square. It is 1 minus 1 minus 2I plus 2I, right? It is 1 by 1 plus u by 1 plus I, right? So it is 1 by 1 plus x. So this is equal to 1 by 2I. It is 1 by 1 plus x, summation of minus 1 to the power n u by 1 plus I, x to the power n with x mode, z mode, u by 1 plus I mode is less than 1. Okay, you see, quite easy. So it is 1 by 2I, summation of minus 1 to the power n. What is your u? U is your z plus I to the power n, and it is 1 plus I to the power n is here with your z plus I mode, u mode. U is here, u mode is less than 1 plus I mode. 1 plus I mode is your root 2. What is your u? U is your z plus I. So z plus I mode is less than root 2. So the radius of convergence is root 2, and this is my answer. Okay, so this is my answer. Is that not easy, right? Is that not easy? It is quite easy. Now coming to another important question, right? If you go on differentiating n times, it is quite difficult here. So I just simplify it. I just divide it. If I divide it, then what will be your fz? It is 2z minus 2, 2z minus 2, and it remains to divide 2z plus 1 by z square plus 1. Now it is a proper fraction. So this will be my 2 into z minus 1. So I can write it here. So the denominator is z into z plus 1. So I try to write it z plus 1 plus z, right? So now you simplify it. If you simplify it, it is 2 by z minus 1, then plus your z by this and this by this. Okay, so this is 1 by z plus your 1 by z plus 1. Okay, so now this is the simplification of the series. This is the simplification of the series. So now what you are asked? You are asked to put center at I. So we need z minus I mode less than r we need. So we put here z minus I is equal to u. So implies here z is equal to I plus u. Now you simplify it. So what is your fz? Fz is equal to your 2 into here I plus u minus 1 plus 1 by I plus u plus 1 by I plus u plus 1. Okay, so I can write it. It is 2 into, it is simply u minus 1 plus I. It is a constant. it will be like this, plus it is 1 by, if I take common I, it is 1 plus u by I, and if I take common here 1 plus I, 1 by 1 plus I, it will be 1 by 1 plus I taken common, 1 plus u by 1 plus I. Okay, so this is equal to, you are getting, so now this will be simply, here it will be simply twice u minus 1 plus I, plus it is 1 by I summation of minus 1 to the power n u by I to the power n, with here it is and here it is 1 by 1 plus I with summation of minus 1 to the power n u by 1 plus I to the power n. And what happens to the radius of convergence? Here u by I mod less than 1, and here u by 1 plus I mod less than 1. So this implies my u mod is less than 1, I mod here is equal to 1, and here it is u mod is less than 1 plus I mod is equal to a root 2 here. Okay, now if I add it finally, what is the minimum of this? So minimum of this is u mod is less than 1 here, right, the minimum of this. So my z minus I mod, u is my z minus I mod is less than here 1 here, the radius of convergence is 1 here. Now just I simply replace, now I simply replace u by here z minus I, then I get the answer. So what will be my answer? It is 2 into, it is my z plus 2I minus 1, and it is plus 1 by I summation of minus 1 to the power n by I to the power n, it is u minus I to the power n, plus it is 1 by 1 plus I summation of minus 1 to the power n by 1 plus I to the power n, and it is here z minus I to the power n with z minus I mod is less than 1. This is the answer. Okay, so the video is getting lengthy because in one shot I tried to tell many things, one shot, right? And here, unless we know this will help us for your most awaited Laurent series expansion, right? So now if z0 is a point of analyticity, is an analytic point, then we find the Taylor series, right? If fz is not analytic at z0, then we use the Laurent series. So in the next lecture I shall discuss the Laurent series. It is very much important, right? It is very much important. So let me to conclude here. If you feel this lecture is useful and interesting, please like and subscribe to my channel. It will boost my motivation to upload subsequent lectures for your benefits. Thank you all. Have a nice day.